Here's another very interesting discussion. Essentially, we don't have to enlarge the stars too much to see what their surface areas are. Currently, astronomers can measure a star's area from the apparent brightness, the star's absolute luminosity, and very importantly, the temperature of the star. In fact, the temperature of the star determines the star's absolute luminosity through the Stefan-Boltzmann law. Well, I won't go into details here, but it's enough to know that astronomers can tell how big the star is without magnifying it. This allows them to determine the exoplanet's size. We still need another important parameter, which is usually the mass of the planet. Planet mass is typically measured indirectly. Namely, let's say, for example, by the Doppler method, meaning the exoplanet orbits around the star, but actually it orbits around a common center of mass. Both of them do. The exoplanet as well as the star orbit around a common center of mass. That means the star moves, it goes forward and backward, and then the light coming from the star will be red shifted when it moves away from us, or blue shifted when it comes toward us. So if we measure the light from the star, the spectrum, we will see an oscillation. The spectrum shifts toward red, then toward blue. And it's very important that the amplitude of this oscillation is a measure of the ratio between the mass of the planet and the mass of the star. Because you realize, if the mass of the planet is very small, then this oscillation has a small amplitude because the star stays roughly in the center. It's true that a star has several exoplanets. So this Doppler motion has several components, but we can decompose this motion into frequency components, and of course we're interested in the frequency component that has a period equal to the orbital period of the planet around the star. So basically from this motion we can also deduce the mass of the exoplanet. And the last thing we're interested in is the planet's atmosphere. We take advantage of the fact that when the exoplanet is in front of the star, the light passes through the exoplanet's atmosphere. And in this way, the absorption spectrum of the light inside the atmosphere can be measured. Some calibrations are done there. Basically, the area of the planet is calibrated against the area of the star, and it's subtracted. So that calibration, and if you subtract those two values, basically you're left only with the light that passed through the atmosphere. And that light that passed through the atmosphere, well, that's specific intensity. You divide it by the intensity of the light coming from behind, which gives you a kind of calibration from the star, and this way you can get the absorption spectrum of the atmosphere. And after the absorption spectrum of the atmosphere is measured, the molecules that are present there are identified. Because each molecule has its own distinctive signatures, some absorption bands at certain frequencies, and in this way, methane, water, and all kinds of other molecules have been found in the atmosphere of distant exoplanets.